I think we're going to just see generational leaps in battery technology quality over the next 5 to 10 years.
The humble battery plays a crucial role in cutting emissions. However, there are still challenges it needs to overcome to reach its full potential.
How do we increase energy density? How do we make batteries safer? How do we make them charge more quickly? And how do we make them last longer?
In this final episode of our first season, we're diving into how batteries play a key role in reaching net zero, some of their surprising uses, and what the future holds for this proven technology.
I'm Dana Clemenson.
And I'm Micah Schweitzer. This is Balancing the Future from METTLER Toledo.
On this show, we delve into the world of science and technology and explore its transformative impact on our lives.
Let's jump in.
The battery's history is all about constant innovation, refining a single powerful idea.
In 1800, Italian physicist Alessandro Volta changed the game with the voltaic pile. That was a stack of zinc and silver discs separated by a saltwater-soaked cloth. This invention sparked the modern battery and set everything in motion.
By 1836, John Frederick Daniell pushed the technology further with the Daniell cell, fixing major issues like polarization. Back then, it was mainly used to power telegraphs for long-distance communication.
We think of today as the age of the electric vehicle, but in fact, the first electric cars, powered by early batteries, already hit the road in the 1800s.
As battery tech grew, it split into two types: primary, single-use, and secondary, rechargeable.
Today, we're focusing on secondary batteries. These play a big role in green energy storage, electric vehicles, and even some airplanes, but we'll get into that later.
There are a lot of different types of batteries out there, so which ones should we be paying attention to in this conversation?
So the classic batteries like the NCM or NCMA, so nickel, manganese, cobalt, aluminium, these are the batteries manufactured by the likes of Panasonic.
That's Simon Taylor. He's the Segment Business Development Manager for Battery Technology here at METTLER Toledo. He spoke to Dana.
So Panasonic manufacture batteries for Tesla. Tesla manufacture batteries themselves in some locations. These are kind of a classic chemistry, and they've been around a long time. The manufacturing process is very stable. They have very high production percentage rates. There's a lot of known technology going on there.
Simon actually started his career as an analytical chemist. He worked in the pharmaceutical industry before coming to our company in 2012.
So you'll hear things like these new 4680 batteries that are coming out from major manufacturers. So this is the width times the height, so 46 millimeters by 80 millimeters high. The classic ones that Tesla have right now are 2170, so 21 millimeters by 70 millimeters tall. There's a big shift from these smaller batteries into higher capacity batteries. So you can use fewer batteries in a car, right, and get better performance. You'll also hear of prismatic cells. So these are big, like household brick-sized batteries. You know, they're typically 10 to 15 centimeters tall, maybe 3-4 centimeters wide and rectangular in shape. So these are typically a little bit safer and a little bit more reliable because you need less of them in a car. And if the car gets hit by something, there's less of a chance that the battery pack will get damaged. So it's not impossible, but it's a safer battery pack. That's in terms of form. Now, in terms of chemistries, there's an awful lot going on. So every region, most every startup company, every customer we're talking to is investigating some new type of battery chemistry. And that could be a way to take the classic NMC chemistries, make them better, or develop completely new chemistries. So lithium-sulfur batteries are on the horizon. Right? There's a couple of big companies with a very well-developed portfolio. So, for example, Lyten would be one in San Diego. They just announced maybe a couple of weeks ago their first gigafactory for lithium-sulfur batteries. So this will be the first time that somebody's industrialized these types of batteries at scale. So that's a really interesting one to look out for. The benefits of lithium-sulfur are they are heavily abundant materials, So sulfur is produced everywhere. You can dig it out of the ground. You can take it from a volcano. You can take it from a lot of manufacturing processes as a byproduct and get very pure amounts of sulfur. So they're cheap. They're very reliable. They have a very high energy density. So they're typically 50% higher than a typical NMC battery. And lithium-sulfur is really very future forwards, I would say. But there are many other technologies. You might hear silicon anode batteries or sodium-ion batteries, and they all have very specific use cases. So sodium is typically a lower energy density, but a much safer battery. So you'll see them in golf carts, for example, or you'll see them in very small cars and vehicles. Silicon anodes, they have a higher energy density, but they're prone to swelling. So when you charge the battery, it swells. So you have to make sure you can contain that pressure in a certain way to keep the chemistry. So the other thing I wanted to say, just to wrap that up basically, is all of these cell chemistries, they sound fantastic. They sound future forwards. They sound like it's the way to go, and it's really the truth. However, validation of these batteries takes a long time. So by the time you send a battery to a Volkswagen or a Rivian or an other producer like Renault, they typically need a minimum of 2 years to validate that battery. So it goes into rugged testing, it goes into charge testing, it goes into all of these processes to ensure that battery is safe. So any technology we read about today could be a minimum of 2 to 3 years away from being industrialized and being released to the market. So that's something you also have to bear in mind. There's a lot of great research going on, but it takes time to industrialize, it takes time to validate, and it takes time to actually build it into a car and get it into the hands of the public.
And these batteries, I can imagine it's not just for cars. What other applications are we looking at?
Not at all. I mean, we're all using one right now, right? We have lithium batteries in our computers, we have them in our headphones, we have them in our mobile phones, but a lot of other technologies are kind of up and coming. So what was it, over the summer, I saw the first lithium battery airplanes flying over Rapperswil here in Switzerland. So they had a fleet of 3 airplanes purely powered by batteries. Now, of course, the flight time was only, I think, 45 minutes or something like that. But with the advent of lithium-sulfur, with these higher energy batteries, you can imagine maybe in our lifetime that we see commercial airliners flying with lithium batteries powering the engines instead of classic kerosene or jet fuel. The other major market that you'll hear a lot of companies talking about providing for is the energy storage market. So we all know that green energy is coming. We're seeing more solar. The growth of solar is huge. The growth of wind is huge. We have things like hydroelectric power. We have tidal power. We have all of these ways of generating energy, but it's kind of useless if you don't use it when it's generated. So we're seeing a lot of growth specifically in the battery energy storage sector. So this is where we have, 2 or 3 gigawatt installations of batteries that are just storing that energy that's created from renewable energy processes and then used later. So used later in the evening, used through the night. So you generate the energy during the day and then you use the energy at night, and this is how you cycle these renewable energies that are maybe slightly less reliable in terms of the ability to generate energy 24/7.
Some countries are already making renewables their main power source. Take Portugal, for example.
In 2024, nearly 3/4 of the country's power came from renewables, mainly wind and hydroelectric. That same year, the Ministry of Energy invested almost 100 million euros to back 500 megawatts of energy storage projects. To put that into perspective, 500 megawatts could power 150,000 homes for a day.
And over in the U.S., the largest battery storage facility ever built opened in Moss Landing, California in 2020. At full capacity, it can store up to 750 megawatts of power. Now, imagine if we could boost how much power a single battery holds. Those numbers could skyrocket. Here's Simon again to explain more.
So in a perfect world, we could maybe double or even triple the capacity of lithium-ion batteries if we could get to that theoretical maximum energy density number through chemistry, through formulations, through whatever, right? Through engineering and so on. So that's why lithium, because it's the third smallest molecule. It carries a charge. It intercalates well. So in other words, it moves across the separator and it kind of embeds itself well in chemistries. That's why lithium. Now, if you want to look at other things like vanadium flow batteries or redox flow batteries, they just use a charge imbalance. So 2 massive tanks of chemicals. And when you discharge one tank, the vanadium ions, for example, they move from one tank to the other side, and that's a charge-discharge cycle. And then when you charge it, you move the ions back into the other tank. So it's more or less the same principle as a lithium-ion battery. You're just using different chemistries and different ways to do it.
And would you say these other types of batteries, like lithium-sulfur, sodium-ion batteries, solid-state batteries, are they an improvement over lithium-ion batteries? Are they changing the landscape in any type of way?
So solid state, I think, for me, it's something that might come before or at the same time as lithium-sulfur. Maybe even a lot of the lithium-sulfur batteries will be solid-state batteries because of the chemistry. Solid-state's an interesting one because it brings a huge number of benefits. So right now, you'll hear a lot about explosion risk or fire risk, or thermal runaway is the industry term for what you hear about batteries, that a battery with such chemistries like NMC or NMCA, they create their own oxygen. So when they catch fire, they self-propagate.
Okay.
That's one of the reasons why we have these so-called thermal runaways. So if you see the videos online, you'll see these Asian scooters, right, that aren't properly manufactured. They're not charged properly. Maybe they're sat out in the sun all day. Suddenly they'll spontaneously catch fire. And the reason they go from zero to volcano is because the batteries generate their own oxygen. So there's almost no way to quench the battery when it starts fire. Now, if you look at a lot of the newer technologies that are in the pipeline, and one of the biggest focuses now is to make sure that doesn't happen. So you can do that with different chemistries. You can do it with different phases of matter. So solid-state batteries, by design, will not encounter a thermal runaway issue because there is no way for the chemistry to spread through the electrolyte or essentially burn itself out. You pierce it, and it remains in the same state it's in, and happy days. And sodium batteries don't have that problem because A, they have a lower energy density, but B, they don't have a capability to generate their own oxygen when they ignite. So there's one of our good customers, they have a video online where they shoot a sodium battery pack with an assault rifle and just nothing happens, right? It's just like a piece of metal. But do that with a lithium-ion battery with classic chemistries and you have a thermal runaway event.
So, but are the sodium batteries not as powerful? So they can't do the same things?
They don't have a higher energy density. They have the same applications, but ultimately they won't have a higher energy density. So you won't find the new Porsche Taycan powered by sodium-ion batteries.
Okay.
But you might find golf carts or simple robotics or even smaller cars, like a one-person car or a two-seater car. That's well within the realms of application for sodium-ion batteries. And there's a lot of customers doing research on making them better, right?
Yeah, what are some of the challenges that customers that we have are facing when it comes to production and R&D in these batteries?
The main challenges are, how do we increase energy density? How do we make batteries safer? How do we make them charge more quickly? And how do we make them last longer? And all of those things boil down to ultimately a lot of chemistry. And without going into too much details, it's really, how are the formulations? What do they look like? How is the battery structured? How do we manufacture the cathodes? There's a lot of detail in there that we could cover over 10 podcasts, but I think ultimately those are the 4 major challenges. It's how do we make those 4 things better?
I can imagine in this type of industry, the information sharing doesn't flow like it would in maybe some of the other sciences. Is that a correct assumption?
To my knowledge, there isn't so much sharing on IP because it's very secretive. Everybody wants to make it big. It's kind of no different to other industries, right?
Yeah, I'm just kind of thinking about in biotech and pharma and health, there's a lot of sharing because everyone's trying to cure cancer. Everyone is researching to make everyone healthier.
Right.
And really, I think because we're all maybe impacted by people who have become unwell. And you could argue that this type of technology could have the same impact on our health.
Absolutely.
Yet there is maybe less of a willingness to all kind of come together to make it,
right,
better for the greater good. It's interesting.
Crises like the COVID-19 pandemic prove how public interest can drive IP sharing. The race to develop a vaccine pushed companies to collaborate like never before.
The battery industry hasn't seen that same level of information sharing yet, but there are efforts underway to change that.
Take the Volta Foundation, for instance. It's working to create a global network of battery professionals.
As rechargeable batteries play a bigger role in the green transition, it'll be interesting to see if this shifts the approach to information sharing.
On that note, Simon sees reasons to be optimistic.
You've seen it now. I think the first time this year, the use of coal in some European countries went down to zero, right? It wasn't just a matter of a percentage, it was zero. And of course, there is still gas. There are still ways of generating electricity using fossil fuels, but we're getting there, right? It's moving forward, maybe not as quickly as I would like to see for my children or in some countries at all. But I think the trend is good, and that gives me some hope, at least. But we talk a lot about vehicles, we talk a lot about energy, but we don't talk a lot about where are all the greenhouse gas emissions coming from? And it's not only energy generation. So, for example, the concrete industry is one of the biggest contributors to global warming. The agriculture industry is a massive contributor. So when we talk about the green energy transition, we also need to bear in mind, hey, we need to find ways to consume energy that doesn't produce greenhouse gases. And that could be using electrolyzers to power a hydrogen furnace to melt steel, right? So there's all these different ways. There's so many different aspects, and it's so complicated.
So are there any environmental downsides, though, to new battery technologies?
Sure, with everything comes a balance, right? There are a lot of people that will say, oh, the mining of cobalt is unethical, right? We hear about children mining it in the Democratic Republic of Congo, and the impact of mining on the environment is huge, and they're not wrong. A lot of the battery companies I talk to now, a lot of these energy companies, they want to find better ways to do this. It's like fair trade for coffee, right? They want to find a way to sustainably mine resources, and they want to find a way to not have these issues of child safety and damaging hundreds of thousands of acres of land by evaporating lithium salt mines. And so there is electrolysis for lithium coming through, extracting it from brine and seawater. There is recycling is on the horizon. So if you look at, there's an amazing quote by the CATL CEO, I think, who said, by 2040 or 2050, China will no longer be reliant on mining raw materials because the amount of recycled material that would be available in the market will be enough to fulfill demand. So there is this circular economy coming, there is this sustainability part coming, but of course, in the first instance, we need enough batteries in the market, we need enough people buying and using cars, we need enough storage systems to run their 15, 20, 25-year lifetime, where we start to recycle those batteries and start to create a true circular economy.
What kind of policies can help support this? Is that an integral piece?
Yeah, ultimately, so we've got the EU battery passport, which is probably one of the most prominent ones right now, which is, I don't remember the details exactly, but essentially what it says is over the course of a period of time, several things need to happen. So there needs to be more and more recycled material going into new battery production. So they've set targets over the next 10, 15 years for companies to adhere to. They've also tried to say, okay, we need to transform some of these, what we would call opaque supply chains, into more transparent supply chains. So this is going in the direction of, ethical mining. It's making sure that we as consumers of batteries, we as people who buy electric vehicles, can scan a QR code on our car and find out exactly where those minerals were mined or recycled. So we know where they come from, what is in the battery, how they were sourced, how they were transported. And this is what the EU has pushed forward rather quickly, I would say, but in a good way. And now there are many other countries that are now looking at this legislation and saying, okay, how do we adapt that? So there will be and I don't call it a battery passport because maybe not everybody calls it that ultimately, but the Chinese government are looking at this battery passport. I think the US and Canada are now looking at some form of legislation. And it helps everyone. It helps us as consumers make better choices. It helps us uncover some of those supply chains that are hidden to us or not really obvious where our materials and where our products come from.
So if I buy an electric vehicle and I drive it for, I don't know, a decade, 15 years, That battery inside the car, does it get recycled? What happens to it?
The first possibility is your battery that's lasted you 15 or 20 years. What will happen is, over the course of many years, if you treat that battery nice, take it out to dinner once in a while. No, if you treat that battery nice, right? And by nice, I mean, the way we work with today's batteries is you don't discharge them to 0 and charge them to 100%. You keep them in this magic range of 20 to 80%. And this is the best, most comfortable dressing gown and slippers area for your battery, right? That's where you're going to keep the lifetime. That's where you're going to keep the best performance. And that's where you should be, right? In this 20 to 80% range. So it may very well be that over the course of a year, the overall capacity in your battery drops 1% or 2%.
Okay.
Just because that's life, right? You will get, the battery chemistry will change with age. And if you always supercharge it, that's never great. You know, a slow charge is sometimes the most sustainable way to keep your battery healthy. But if you're driving from here to the UK, 1,000 miles, you might want to supercharge it because you might only want to take a 10-minute break instead of a 30-minute break or something like that. So ultimately, what's going to happen to your battery? Your battery is probably, I would say, highly likely going to go into an energy storage application, because the lifetime of that battery for energy storage is maybe 20 more years on top of what you've used it for in those 10 years.
Okay.
Because it's a low demand application. It's a slow charge, it's a slow discharge. The overall capacity of that battery is not that critical. And they will bring it into what's called a second life. So your first life is in the car, second life is in an energy storage system, third would be recycling. So when that battery is really, really out of luck, it's really on its last legs, it's ready for its pension, then you send it off to the recyclers.
How does the supply chain work with that? Because I can just, the way things have always been, your car doesn't work anymore. It ends up in a compound. What do they call it?
A scrapyard or something like that, right?
A scrapyard, that's it. Yeah.
Exactly.
And so it's probably not quite safe to do that.
No, you would 100% take the battery pack out. So I think the way the cars are being designed these days is that you can literally unscrew the battery pack and either replace it, right? So I don't know that there's so much focus on, hey, what happens to my car when I want a new battery pack? I think there are some companies working on the principle now that, my first car that I bought in 1999 probably was dead on its feet in 4 to 5 years. The car I bought 10 years ago that I'm now thinking about replacing still behaves like a brand new car.
Right.
And so the overall lifetime of everything we're using now is getting longer. So maybe not in some areas, right? Some consumer electronics are designed to fail after 3 or 4 years to keep the prices low.
Right.
But I mean, certainly I think any car you've bought in the last 5 or 6 years is going to last a long time. So why not think about just putting a new battery pack in your car and then it has an entirely new lease of life instead of taking it to the scrapyard?
Yeah, I'm just trying to think of the role that the car manufacturers have in that too, because, you don't want every year to come out with something latest and greatest and entice people to, want a new car every 5 years anymore.
Exactly. I think we're going to just see generational leaps in battery technology quality over the next 5 to 10 years. And there will be a point where people are no longer talking about so-called range anxiety. How long do I have before my battery runs out, right? That's what they call range anxiety in the EV world. That won't be an issue 5 years from now. Nobody will care that their car does 500 or 700 miles because it would just become normal and it's acceptable. And battery technology will get better so people can charge more quickly.
Which of the current developments in battery technology are you most excited about?
In terms of battery technology itself, I think the lithium-sulfur for me is going to be a big one. I really see that as being safe and high energy and charging well. They have some chemistry stuff to get over, like I said earlier, but I think that's going to be a big change. I'm not saying it's the future, but I'm saying it's probably, for me, it's one of the most promising ones right now. I think solid state will come first. There's a lot of companies that are working on that, and there's a big challenge to industrialize it. It's fairly difficult to get these gels and these polymers and these ceramics in an industrialized process, but they're working on it. They're moving it forward. First prototypes are out there. But what I most like is I most enjoy talking to customers, hearing what challenges they have, trying to understand how they want to move the processes forward. And one of the best things for me about working in this industry is everyone is just so passionate. Everybody battery chemist you meet, every battery engineer, every process development guy, they're all like, we're doing this because we believe, right? We want to go forward. We want to be a part of this. We want to change things. And every customer I speak to has the same attitude. And it's just really refreshing to see that so many people believe we can do it and we can get there.
I want to ask a question that we ask all of our guests.
Mm-hmm.
What advice do you have to young scientists who, might also be looking outside of the lab to further their careers?
So when I went to university, there was chemistry, there was chemical engineering, there was biochemistry, there was chemistry with management and chemistry with business. And the question I always asked myself back then, when I was so inexperienced, is how the hell does chemistry and business work?
Right.
How does chemistry and management work? But, we get students here now from the University of Zurich, and it's so amazing for people that want to move into a more commercial or instrument-based future. And it really meshes together. So what advice would I give to those people? Be curious. One of the things that's always served me well over the years is I'm going to get a bit big-headed, but my ability to be curious. Whenever I'm with a customer, I might annoy them every now and again, but for me, it's about learning and understanding. If I can stand in front of a customer and ask questions and understand what they're trying to achieve, why they're trying to achieve it, where we can go from here, how can we help, why is that important to them, where are the bottlenecks? That natural curiosity led me away from the lab. Because I said to myself, okay, what if I put myself on the other side of the fence? What if I'm the guy coming into the lab, showing you how the equipment works and showing you how you can be more efficient, how you can do things better? I don't want to say better, but how you could be more efficient or more productive or do things differently to make the end of your day more happy, right? And that was the question I kind of asked myself when I moved out of the lab. I thought, what if I want something more than this? Because it was clear to me I was never going to be a research chemist. I have a quality background. A lot of quality is ensuring you do the same things every day to hit a certain quality target. And I knew for me that wasn't satisfying my curiosity. And I thought, right, it's time to make that change. It's time to move on.
We've been speaking with Simon Taylor. He's the segment business development manager for battery technology here at METTLER Toledo.
Micah, you weren't here for this conversation, but listening back to it, what were your key takeaways?
One of the things that's really fascinating to me is that we're fundamentally still working with a more than 200-year-old technology. If you think that the basic battery was developed in 1800, we still have the same pieces in place, an anode, a cathode, the electrolyte. But there is seemingly an endless amount of innovation that is still possible within those parameters.
I think one exciting part is the whole idea behind energy storage and how much energy we can actually store into these batteries. Because as this increases, we'll have many more applications for batteries and their technology.
And of course, to create these batteries that have significant energy storage potential or lightweight or compact sizes, we're looking at how to mine and collect different materials. And these, of course, have their own challenges associated with them in terms of environmental concerns and labor concerns. And so there's also a lot of room for innovation and development on that front as well.
I couldn't agree more, Micah. And that's it for Season 1 of Balancing the Future from METTLER Toledo.
As we gear up for Season 2, what questions about science and technology do you have?
Let us know by leaving a review, or if you're a Spotify user, leave us a message in the comments section.
And be sure to subscribe wherever you get your podcasts.
Now keep an eye on your feed for the Season 2 trailer, and thank you so much for listening.